All right, hi, welcome back to 10600. So the first thing that I wanted to do today was to talk a little bit about the exercise that's due tonight. So if you have questions about the exercise, please feel free to ask us. What I'm going to do is I'm going to solve a related problem for you guys here, and hopefully seeing how I solve the related problem will help you with the exercise. So let's go ahead and get started. So the first thing, I've posted this code to Piazza so that you guys can follow along. Whoop. So hopefully this is big enough font that everybody can see. So let me show you first what this does. We'll get a figure window here. Ignore what's in the figure window currently. We'll get to that later. But what that does is the following. All right. So what are we looking at here? We are trying to fit a distribution over the integers between -20 and 20, and we're going to fit it by maximum entropy. And what I'm showing is the distribution as we go through different steps of gradient ascent. So let me run that again. It looks like the animation is actually a little bit choppier than I was hoping that it would be, but that's okay, I guess. You can see that it starts out fairly flat, and relatively rapidly we get this sort of characteristic bump shape that it converges towards. All right, so let me move that over like this, and we'll take a look at the code, and so you can see what's going to happen. All right, so this line here, I've posted the code to Piazza. This line here sets up the set of points that we're going to have a distribution over. It's the integers from -20 to 20. Here are the features that we're using. So it's the points and the points squared times a constant, right? And so that means that this is the vector t that we looked at in the lecture notes last time. So for every point in our domain here, there are 41 of them, I'm going to have a vector t which has the x for that point and the x squared for that point times a constant, right? And so this is the setup for maximum entropy. Then if we want to actually do maximum entropy, we need a random sample. So here's a sample of from our distribution, right? It's a bunch of integers that are between -20 and 20, -5, -6, 2, -1, 4, -6, 2, right? So some are repeated, so like -6 happens twice, and 2 happens twice. It looks like all of the other ones happen only once. And given this sample, our goal is going to be to use maximum entropy to fit a distribution to it, using the features that we just defined right here. So the first thing that I'm going to do is I'm going to count how often each one of our x's happens. So you don't need to understand this is a MATLAB idiom, but what's going to happen is that this is going to create a vector of length 41, and each element of the vector will correspond to one of these guys here, and the entry there will say how often that value occurred. So for example, in the entry corresponding to -5, there'll be a 1, and in the entry corresponding to -6, there'll be a 2, and in the entry corresponding to -20, there'll be a 0, because -20 doesn't appear in this sample. All right? And so here, now, what I'm doing is calculating the average, the actual observed average value of the feature. So if you remember from maximum entropy, we had one of the things that we needed was the actual observed value, observed average value of our features in the sample, and that's this, right? So what it's doing is features transpose times count. What that does is it takes each row of features and it counts it a number of times equal to the corresponding entry of counts. And then I divide by the total number of samples, which is the sum of the entries and counts. All right, now we're going to do maximum likelihood. So we're going to start with our parameter vector at 0, or I guess the 0, 0, the length 2, 0 vector. The reason it's length 2 is because there are 2 features up here. And we're going to do 400 iterations of gradient descent. And in each iteration, we're going to calculate what is our probability distribution right now, right? So we know that in maximum entropy, we're going to get, and that the solution is going to be an element of an exponential family. It's going to be e to the features times parameters, right? And so I just compute e to the features times parameters. This gives me a vector, again, of length 41, and I can normalize it to get our probability distribution. This is equivalent to calculating the g of theta, the normalizing factor. And now I have a probability distribution over my features. I can calculate the expected value of that probability distribution. You don't actually need this here, but this is just in case we're interested. It's helping us tell the progress of our maximization, basically what is the likelihood at the current time, the log likelihood. And now we're going to compute the gradient, right? So the gradient is n times the difference between the observed and the predicted feature values. And we're actually going to skip the factor n and absorb it into the learning rate later. So here's the calculation of the gradient. And then here's the gradient descent. And I'm using the learning rate 0.01 adjusted by that factor of n. And I just make an update. And then every 5 iterations, I report progress. And so if you look, I'll show you, right? This is what the output looks like. Right now, we've basically converged, like 400 iterations is way more than we actually need. And I'm showing the iteration number, the likelihood, log likelihood value, and the values of the 2 parameters. This is the one that corresponds to the feature x, and this is the one that corresponds to x squared over 20. So if we scroll up back towards the beginning, right? So we start at a worse, lower log likelihood value, right? Ignore the 400 there, right? So this is where we started. We started a worse log likelihood value, slightly different thetas, and as we optimize, we eventually converge towards our final value of theta. And we're basically there by a couple hundred iterations, but it keeps changing slightly for the length of the run. So if I'll take that back off of the display, and if I run it again, you should be able to see. Wow. So the animation goes a lot slower now that I'm broadcasting. I guess broadcasting uses a bunch of CPU, but it's a lot slower and choppier than it was when I looked at it. But it still looks like you can see what's going on. All right, so hopefully this helps people understand what's going on in the homework assignment, right? We're trying to estimate a distribution. In the homework assignment, it's over the set of integers between, I think it was 29 and 80, basically a lower and an upper bound. Here we have a different lower and upper bound. And in the homework, we give you a list of, I think it was 11 features. Here I'm just using 2 features, but again, the idea is the same. And we're trying to fit a distribution that achieves a particular expected value for the features. And so if you, let me bring this back here, right? If I print out what the observed value of the features is, right? It's the average of x is minus 1.43, and the average value of x squared over 20 is 0.87. And if here's the corresponding values for the distribution here, the one that I'm plotting, right? If you calculate those expected values, they almost exactly match. So our optimization has succeeded approximately in getting the distribution that we want. Okay. So please continue to ask questions and stop me. I'll stop going over notes and try and answer them if we get questions that come in. But hopefully that should help everybody do a good job on the homework that's due tonight. All right. So let's take Piazza back off. All right. So now, last time around, we were modeling discrete random variables, and I want to spend this lecture talking about how to model a continuous random variable. So as before, what I mean by modeling is coming up with a probability distribution that describes the behavior of that variable. And typically the probability distribution will have some parameters in it, and our goal will be to estimate those parameters. So let me start by reminding everybody what it means to be a continuous probability distribution, right? So these are the notes from before on probability densities. I've updated them a little bit in case anybody wants to go back and look, but I just want to go over the first few sections again to make sure everybody's on the same page. So if you have a continuous random variable, the simplest thing that you could do with it is discretize it. So you could pretend that there's some minimum increment that you can measure, call it epsilon, and round your variable to the nearest multiple of epsilon, and then it becomes a discrete random variable. You go from very small, very negative multiples of epsilon to very positive multiples of epsilon, but there's a discrete set, possibly even a finite set of possible values. And this is not practical typically, but if you're confused about a continuous random variable, you should almost always go back and try and think of it in terms of a discrete version. So the difference between continuous and discrete is if you have a continuous random variable, it doesn't make sense at all to think about what the probability of getting some particular value is, right? The probability that your height is exactly 6 feet and 1.3725 inches is 0. Not just small, but 0, because there are infinitely many possible real numbers, and so you can't have them have finite probability, otherwise you'd have infinite total probability. So what we do instead is we work with a probability density, right? And so a density is defined by the following equation. Suppose that there exists some function f such that you can compute probabilities of events by integrating f over the event. Right? So here's an example here. The function f is 1 over square root of 2 pi e to the minus x squared over 2. And if we can compute the probability that our variable goes between 0 and 1, happens to be bigger than 0 and smaller than 1, by doing this integral from 0 to 1 of f of x dx. If that's true, then we say that f is the density for x. This particular example happens to be a Gaussian density, and we'll talk more later today about Gaussian distributions. So that's what it means to be a density. And a density acts like the derivative of probability, right? So densities are not probabilities, and many mistakes can be made by confusing the two of them. Instead, we're going to, when we work with a density, we have to integrate the density to get a probability. And in particular, this is a concept that I hadn't discussed before, but it's probably familiar to a lot of you. There's something called a cumulative distribution function, which is the integral of the density starting at the lowest possible value, in this case minus infinity, and going up to some upper limit x. And so if I perform that integral for the Gaussian density above, you get something that looks like this. It's always an S-shaped curve that starts off at 0, right? The probability that you get minus infinity or smaller is 0. The probability that you get plus infinity or smaller is 1, and so the upper limit is always 1, and then it always goes monotonically increasing in some functional form until we get to the upper limit, right? And here this is a Gaussian distribution, and so it's nice and smooth. You can get a lot funnier looking CDFs, but this is a pretty standard one. All right, and so when I say that the density is the derivative of probability, this is what I mean. The CDF, if we look at the CDF, it's the integral of the density, and so by the fundamental theorem of calculus, the density is the derivative of the CDF. And since the CDF is a probability, the density is the derivative of probability. All right, that's everything that I wanted to review about densities. So again, please feel free to ask questions, but we'll leave densities behind for now. And we will go instead to working with continuous variables. So here we go. All right, so there's, just like with discrete, there's a fair variety of standard families of densities for continuous random variables. So I'm going to go through a few of those, by no means all of them. If you want all of them, well, you'll be waiting a long time because there are a lot, but you can always look them up on Wikipedia or in the back of a probability textbook. But then after I go through a few examples, I'm going to talk about some general strategies for coming up with probability densities. And just like the discrete case, maximum entropy is probably the most important of those. All right. So just as a warm-up, let's look at the uniform distribution, right? So here is a uniform distribution. It's 0 outside some interval. Here the interval -1 to 2, and it's constant within that interval. And the constant is chosen so that the integral over the interval is 1, right? So here the length of the interval is 3, and so if we choose it to be a third, it integrates to 1 over the interval. Not much to say about that, except it's a useful distribution if all you know is sort of the range that is possible for your random variable. The next one I want to mention is the normal distribution. Oh, I just realized I don't think that I posted this set of lecture notes to Piazza. Let me go and post it so that people can follow along if they would like. Sorry for the delay. So I just posted the lecture notes on Piazza. It's now, oh, and I see people are now starting to ask me that question, so sorry about that. I've posted it now. The lecture notes are linked from the syllabus post on Piazza. All right, so here we go. The normal distribution. So just like, yeah, all right. So for the normal distribution, it's probably the single most used distribution in the entire world of machine learning. It's called normal or Gaussian. Gaussian after Carl Friedrich Gauss, the guy who invented it. And it's really almost the default for modeling a continuous variable. There are several reasons that it's so popular. One is that it's analytically really easy to deal with. We'll see that as we try and deal with it. But another is that it arises very naturally in some common situations. So the first of those situations is called the central limit theorem, which we'll talk about in a sec. And the second is that it's closed under two common operations, addition and scalar multiplication. So what do I mean by closed? That means that if you take normal distributions and you add them together or multiply them by a scalar, the result is going to still be a normal distribution. And that's really pretty convenient when you're trying to work with distributions, because it means you don't have to deal with a huge variety of different families of distributions. You can just assume that you start off with normal distributions and then you add and multiply them together, and you add them together and you scalar multiply them, and you stay within the family of normals. All right, so that's why normal is popular. What does normal look like? It's probably known to a bunch of you, but it's the famous bell curve, right? So this is the density of a normal distribution. It's centered at the mean, which is in this case 0. And the width is more or less 2 times sigma, where sigma is the standard deviation. And in this case, that's 1, so it goes from about -2 to 2, right? And by width, I mean the part of the distribution that has a decently high probability. If you want to be precise, between 95% of the mass of a normal distribution is between plus and minus 1.96 times sigma, right? So the parameters here are mu and sigma squared, mean and variance. Square root of variance is sigma, called the standard deviation. Mean shifts the distribution left and right. So this one has mean 0. If we went like, this, it would be mean 2. And standard deviation here is 1. And if we increase the standard deviation, that would mean that it goes down slower like this. And if we decrease the standard deviation, it would go down faster like that. All right? So I said that random variables are closed under addition and scalar multiplication. It's actually useful to be able to figure out how the parameters change. So it's actually really simple. Means add and standard deviations add. So in particular, if you add together 2 or more random variables, they don't actually even have to be normal, but if they're normal, the mean of the sum is the sum of the means. So if you add 1 of mean 2 to 1 of mean 3, you'll get 1 of mean 5. And if you scalar, when you're adding them together, you also need to know how the variance transforms. And as long as the variables are independent, the variance of the sum is the sum of the variances. So when you add them together, the mean sum and the variances sum. And then the other transformation is scalar multiple, and that will scale the mean and the standard deviation. So the mean of kx is k times mu, and the standard deviation of kx is k times sigma. Right? And that means that the variance is k squared sigma squared. All right. So let's get to the central limit theorem. So if you remember, when you're adding together a bunch of random variables, their means add and their variances add. And then when you scalar multiply, that reduces the variance. and well, sorry, that scales the variance. So let me just show what happens if I take the mean of a whole bunch of random variables, right? So if I have x1, x2 up to xn, and I take x bar is 1 over n, sum from I equals 1 to n of xi, right? So then let's suppose that they have means mu I and variances sigma I squared, right? Then the mean of the sum of the xi is equal to the sum of the means of the xi, which is just mu I equals 1 to n, right? And the variance of the sum of the xi, let's assume again that these are independent. This is equal to sum from I equals 1 to n sigma I squared, right? So then the mean of the average, e of 1 over n sum of xi, sum over I. So the mean scales, right? So this is 1 over n sum over I of mu I, right? So it's just the average of the means. And then the variance of sum over I xi times 1 over n is equal to, well, so when you scale a random variable, its standard deviation scales, which means its variance scales by the square of the scaling factor. So that's 1 over n squared sum over I of sigma I squared, which is equal to, I'm just going to break apart the 1 over n squared into 1 over n times 1 over n, right? So if you look at this is the mean of the variances, right? And so when you average a bunch of them, the variance keeps going down, right? So let's say all of the sigma I were equal, then this would be just sigma squared, right? This would be constant, and this would be decreasing. So the overall variance would be going down proportional to the number of, to 1 over the number of terms in the average, right? All right. So that's an important behavior, right? If you average together a whole bunch of things, let's say they all have the same mean and the same variance, well, the mean will stay the same, right? The expected value will always just be the average of all of the means, and if the means are the same, that's just going to be constant. And the variance is going to be decreasing, like 1 over n. All right. So that just tells you the mean and the variance. What the central limit theorem says, which is kind of cool, is that in addition to knowing what the mean and the variance are of the average, you can say something about the distribution of the average. And in particular, the distribution becomes closer and closer to normal the more terms there are in the average, so long as the individual variances are not too far apart from one another. All right? So, for example, suppose that we were to flip a biased coin a whole bunch of time. Each one of the flips would itself be very far from normal, right? Each flip is a Bernoulli, and that's not at all close to a normal distribution. But if we take the average of a whole bunch of flips, we're going to get something that looks a lot like a normal distribution. And what I've done here, is I've plotted, okay, so here's the mean of coin flips. And what I've plotted, the blue line here, the staircase-looking one, is an empirical approximation to the cumulative distribution function of the mean of 50 flips, right? So the reason it's staircase-looking is that there's a discrete set of values that the mean can be. It can be 0 over 50, 1 over 50, 2. Sorry, I'm getting a question. What are the different means coming from? So what I'm saying here is that the expected value of I is equal to mu I, and the variance of xi is equal to sigma I squared, right? So each one of these x's has a mean and a variance, and I'm just writing mu I for the mean of the ith one, and sigma I squared for the variance of the ith one, right? And so the mean, so if each one of these xi is a random variable, the mean of all of them is also a random variable, right? Because when you add together, anytime you take functions of random variables, you get another random variable. In particular, if we were to repeat this experiment of drawing n samples and taking their mean, we would get a different value the next time, right? And so because x bar is a random variable, we can ask what its mean and variance are, right? This is, and the answer is here. E of x bar is equal to that, and the variance of x bar is equal to that. Right? So we can calculate the mean and variance. In particular, if we look at the coin flips, right? So suppose xi is distributed as Bernoulli, with probability p, right? Then the mean of xi, which is mu I, that's just p, right? And the variance of xi, that's equal to sigma I squared. You can look this up, or I happen to remember the formula. It's p times 1 minus p, right? And so if I add together 50 of these, right, if I take the mean of 50 of these, E of x bar is still going to be p, and the variance of x bar is going to be 1 over 50 times p times 1 minus p, right? All right, and so the red line in this figure here is the cumulative, the CDF of a normal distribution with this mean and variance. I took p equal to 0.3, and so I can plot the plot that. The for the coin flips, I can just run the experiment a lot of times and count how often the mean is 0.1, 0.2, 0.3, 0.4, and so forth, right? And if I plot how often the mean is less than x for each value of x, I'll get this staircase-looking CDF. And the reason it's a staircase is because there's a discrete set of possible values that the mean could take, right? The mean of 50 coin flips, each one can be only 1 or 0, and so the mean can be 0 over 50, 1 over 50, up to 49 over 50, 50 over 50, right? So there's 50 possible values that it could take, and the height of each of the stair steps is how often the mean takes that value. And you can see that the blue line, despite being staircasey, is very close to the red line, meaning that the normal approximation is actually quite good, right? So that's a surprising and wonderful fact about taking averages of lots of variables, right? You can almost always, if you have enough terms in the average and the terms don't have wildly different variances, you can almost always approximate quite well with a normal distribution. Here I'm taking an average of only 50 terms, and already I'm quite, extremely close to being a normal distribution. So that is probably one of the biggest reasons why normals are so popular, because they're a good model for the mean of a bunch of approximately equal contributions. Another example might be if you look at a person's height, right? So there's a whole bunch of genetic and environmental factors that affect height, and there are only a few of these factors have an individual influence that's significant. So if you get rid of those individual factors by, let's say, selecting people for whom they're all the same. So for example, you select people who are all male so that the factor of gender doesn't influence height. If you do that, then the resulting distribution over heights is going to be really close to normal. All right. So this is maybe not particularly useful, but it's simple, so I wanted to mention it. It's very easy to make a model of a continuous random variable by picking a piecewise constant density. That's basically saying that you pick a bunch of cutoffs and then say that the distribution is uniform between every pair of adjacent cutoffs, and so you'll get a density function that looks like this. And the result is a lot like a histogram. So that's kind of a useful, right? So, you know, you can imagine a histogram that looks very much like this distribution. And so you can imagine estimating a distribution like this by building a histogram from some data. All right. So the next distribution that I would like to describe is the Dirichlet distribution. So a lot of times, so you remember in the discrete distributions, we talked about categorical and multinomial distributions, right? So a categorical distribution was a distribution whose outcome was a number from 1 through k, specifying which of k discrete outcomes happened. And so the answer would just be, you know, I got a 3 or I got a 5, right? And a multinomial, the distribution was the result of sampling from a categorical distribution a bunch of times and counting how often each one of the outcomes appeared. And so a single sample from a multinomial looks like a vector of counts. You would say, you know, I got outcome 1 7 times, outcome 2 12 times, and so forth up to outcome k. And that would be one sample from a multinomial. In both a categorical and a multinomial distribution, we need a vector of probabilities as a parameter, right? You have to know what's the probability of each of the individual outcomes. So if I want to make a distribution over that vector of probabilities, one answer to that problem is to use a Dirichlet distribution. A Dirichlet distribution has this form, which is maybe, you know, it is what it is, but this is the form of a Dirichlet. The parameters of the Dirichlet are these alphas, these exponents here, right? So the probability of getting a sample, which is a vector of probabilities that's, you know, each of them is bigger than 0 and they all sum to 1, you get by raising each probability to the power of the corresponding exponent and then normalizing, right? So it's a useful distribution because it's fairly often that we're trying to estimate some probabilities. And in fact, Dirichlets arise very naturally when you're estimating probabilities because if you observe n categorical samples according to probabilities p, and if you start from a uniform prior over p, then our posterior distribution will be Dirichlet. And in fact, the parameter of the posterior distribution will be the vector of counts. So let's maybe derive that just to make sure that everybody gets what's going on, right? So if we have a bunch of samples, xi is distributed as categorical with parameters p, right? And p is a vector in Rk with p bigger than or equal to 0 and the sum over j, pj equal 1, right? And we have a sample x1 through xn. then the probability of that sample is going to be, well, let's write the count j is equal to the number of times outcome j happens, which is the sum from I equals 1 to n of the indicator of whether xi happens to be equal to j. Right? So these are just the counts, and so the counts, x's are categoricals, the counts are going to follow a multinomial. The probability of our data set, right, so I'm going to say L, the likelihood, is equal to the product over all I of P sub xi, right? So I'm going to take, if xi is 3, I'm going to count p3. If xi is 7, I'm going to count p7, right? And so that's equal to p1 to the c1 times p2 to the c2 up to pk to the ck, right? Now our posterior will be proportional to our prior times our likelihood. We just said that our prior is uniform, and so it's going to be proportional to the likelihood, right? Which we just said was p1 to the c1 up to pk to the ck, right? And so now, if we look over here, that's exactly the distribution. That's exactly going to be a Dirichlet distribution. Right. With parameters alpha j equals cj, right? So each one of the alphas is going to be one of the counts, right? And the reason we know that the posterior is Dirichlet is because every term that involves the p's matches form with the likelihood here. And therefore, the only possible normalizing constant is going to be this one, right? We know that this succeeds in normalizing it to be a probability density, and there's only going to be one, and so it must be that one. Okay? So what that means is that the parameters of a Dirichlet, you can think of them as being counts, right? Either they're explicit counts, we actually did an experiment and observed, you know, alpha 2 copies of outcome 2, or we have a Dirichlet, somebody just tells us that the right distribution is Dirichlet, in which case we can think of that information as being equivalent to having seen an experiment in which we had alpha 2 copies of P2 and so forth. All right. So that's kind of useful to be able to make a distribution over a vector of probabilities. So just as you guys are currently doing maximum entropy for discrete variables, we can also do maximum entropy for continuous variables, and it's almost exactly the same. So let me just go over it and make comparisons to what the discrete case looks like. So what the so just like in the discrete case, we're going to define a vector of features t of x, and it's going to depend on our continuous random variable x. So for example, we might set t of x to be x and x squared. And just like before, we're going to describe the distribution of x using the mean parameter, which is just the expected value of t of x when x is sampled according to our distribution, and we'll call that t bar. And given t bar, the Maxent distribution is the one that maximizes entropy, subject to the constraint that it matches the the mean parameter t bar, right? So just like before, E of t of x is called a moment, and so this vector of moments has to match our observed vector of moments. And just like in the discrete case, we don't have to do maximum entropy. We can start from some base distribution P0, and we can try and minimize KL distribution from P0. And if we choose P0 to be uniform, the KL divergence from uniform is the negative of entropy, and so maximizing entropy is the same as minimizing KL divergence. And we have just like in the discrete case, there's an explicit expression for the Maxent distribution, or the minimum relative entropy distribution. And it's, in fact, it looks exactly the same. It's the base distribution times e to the t of x dot theta minus a normalizing constant. And theta is again called the natural parameter. And again, we can show that g prime of theta has to be equal to t bar if we're going to satisfy this constraint that e of t of x has to be t bar. And we can solve exactly the same way, just like you guys are doing gradient descent, for example, to accomplish maximum entropy in a discrete distribution. You can do it equally well in a continuous distribution. However, there's a wrinkle. You guys are computing the normalizing constant g of theta. You can compute it just by summing over all of the possible discrete outcomes. In the continuous case, you have to compute the normalizing constant by doing an integral. And that integral might be easy or hard or basically impossible, right? So Maxent in the continuous case is limited by our ability to compute this normalizing constant efficiently. And in fact, if you go on in machine learning, there's a lot of machine learning methods whose goal is to be able to calculate g of theta or to approximate g of theta efficiently. Now, there is one important difference from the finite case, which is that for some values of theta, it might be impossible to normalize the distribution. For example, suppose that t of x is just x, right? And let's say, well, here I'll write out one. Suppose that we have p0 of x is proportional to, I don't know, 1 over x squared, right? And x is allowed to be in 0 infinity, right? Meaning r plus. So this is a perfectly valid distribution. You can normalize 1 over x squared because its integral is finite over r plus, right? If we take t of x just to be x, right? Then we take theta to be 2, right? Then our distribution would be 1 over x squared e to the 2x minus g of theta. Now, can we compute a g of theta so that this is normalized to be a probability distribution? The answer is no, right? Because e to the 2x increases really, really quickly. Its integral is infinite, right? And so there's no way to compute a finite number g of theta, right? There's no way to compute a finite number g of theta to normalize this. So we cannot have theta equal 2 in this situation. So there's going to be some set capital theta of valid values of theta, little theta, and we're just going to constrain little theta to be in that set. And that's not a problem because just like before, we're going to be able to achieve any achievable value of e of t of x by some theta in big theta. So the normal and the Dirichlet families that I talked about before, these are in fact examples of exponential families. The normal distribution is based on the statistics x and x squared, and the Dirichlet uses the log probabilities. And it's an interesting exercise to try and convince yourself that those distributions are exponential families using these values of t. All right. So there's a particular type of distribution that turns out to be important to mention, which is the power law distributions. So if we have a feasible range of x's that goes from some minimum x up to plus infinity, and we take our statistic to be minus the log of x, actually I should say t equals minus the log, can't write today, minus the log of x over x min, right? Otherwise you might so here x is in x min up to infinity, right? So you need to normalize by x min, otherwise you might take the log of a negative number. If we use that statistic, then you get a class of distributions. So for the rest, for here, let's just suppose x min is 0. Sorry, x min is 1, so its log is 0. You get a distribution that looks like e to the minus theta times t, e to the theta times t of x, which is minus log x, minus g of theta. So e to the minus theta log x is the same as x to the minus theta, and then this is a constant with respect to x. So you'll get a distribution where the density decreases as a power of x, the minus theta power of x. And so the name power law comes from that. Somebody is asking, sorry, how to compute the derivative of log likelihood with respect to theta. I'm going to assume that that means in the context of an exponential family up here, right? Actually, I'm not sure that I understand the question. So the question is how to compute the derivative of log likelihood with respect to theta, but in what situation? In a normal distribution, in an exponential family, in a power law? So maybe if we can make the question a little bit more precise, I can try and answer it. Until then, let's get back to power laws, right? So the density of a power law distribution is a power law in X, and that's where the name comes from. And the importance of it is that a lot of natural phenomena seem to follow power law distributions. So people have tried to use power law distributions to model things like what is the strength of an earthquake in terms of the total amount of energy released, or the property damage due to a hurricane in, let's say, constant 1987 US dollars. So you can derive the CDF of a power law by integrating. It happens to take this form. And the CDF, 1 minus the CDF, is also a power law, right? Because the integral of x to the minus theta is a constant multiple of x to the minus theta plus 1. So power laws are interesting because they have this property called heavy tails, which means basically that so let's see, the tail is basically the probability of extreme values of x, which in this case means really large values of x. And the probability of more extreme events has to decrease, otherwise you couldn't have a finite integral. But it can decrease quickly or slowly. And if it decreases slowly, you have a heavy tail, and if it decreases quickly, you have a light tail. And so if you look at, let's say, a normal distribution, right, the probability goes down like e to the minus x squared, or like e to the minus a multiple of x squared, which is really, really fast, right? Big values of x become nearly impossible. Whereas if you look at a power law distribution, it could go down only as like x to the minus 2, for example. And so that's a big difference, right? So you can have the probability of these extreme events goes down much, much more slowly for a power law than it does for a normal. And empirically, that makes a big difference because if we try to model a heavy-tailed distribution with a light-tailed model, we're going to systematically underestimate the probability of rare extreme events, right? And so that could cause a real difference from between the real world and our model. So for example, think of an insurance company that's trying to reason about hurricane damage. If it systematically underestimates the probability of very large, very damaging hurricanes, it's going to go out of business very quickly. All right. So I've described a lot of different distributions that you could use to model a continuous variable. And the question that you should be asking, I guess, is how to pick one of these for whatever situation you find yourself in. You need to make a model of some variable x, and you know some stuff about x, and how do you decide which distribution to pick? And so I guess the decision procedure goes something like this. First, you look for a family of distributions that somebody's defined ahead of you that has the right properties. So for example, if we're modeling a vector of probabilities, you should maybe strongly consider using a Dirichlet distribution to model that. Maybe there'd be a reason not to, but at least that should be something you consider. Same thing, if you have some thing that you're measuring that you think is influenced by a lot of small additive influences, you might try modeling it as a normal distribution. Or if you're modeling some heavy-tailed phenomenon, you can consider a power law, right? And I've listed a few of these, but again, there's, if you're in this situation, you can flip to the back of a probability textbook and just page through pages and pages of distributions that people have designed for different purposes. So, there's a Weibull or an exponential, or like negative, I don't know. There's a lot of different distributions that you could use. And so it's worth just looking through some of the common ones and seeing if they match your case. If you can't find a predefined family, you have a couple of options. One is that you can look for a transformation that brings your variable into a predefined family. So I haven't really talked about that yet, but for example, one common thing that people use to model distributions is called a log normal. A variable follows a log normal distribution if the log x follows a log normal distribution if log of x follows a normal distribution. Meaning that if you take a normal random variate and raise it to take exp of that normal random variate, you get a log normal random variate. But second, and maybe more importantly, we can use tools like Maxent to try to build our own family of distributions that's good for modeling. So in particular, if we're going to do Maxent, what we want to do is pick some relevant features that we can use as moments, right? So for the normal, we picked x and x squared. For other situations, you might have problem-specific intuition that lets you figure out what the appropriate features are. Like, for example, in the homework problem, it could be we have an intuition that the day of week influences how likely a homework is to be due on that day. And so we pick day of week as a feature. And then once we have the relevant list of features, we can build our own family using Maxent or using minimum relative entropy. So, let's see. I had an exercise that I was thinking of handing out today, but I think it may be too close to the end of class to do that. So let me just talk a little bit about some of the things that you will need to know, and possibly we'll hand out the exercise in our next class. So if you want, so let's say we have a sample, x1 up to xn, right? And we think that they're distributed according to some probability distribution p of x. So how can we, one very useful tool for figuring out what p of x is would be the cumulative distribution function, right? Because there's a one-to-one relationship between probability distributions and their CDFs. And so if we knew the CDF, we would get the distribution back. Now, of course, we can't know the CDF exactly. We just have a sample. But one thing that we can do is we can estimate the CDF from the sample, right? So the CDF, f of x, is equal to the probability that our random variable is less than or equal to x, right? And we can estimate that, that's approximately equal to the fraction of the sample that's less than x, right? So that's the 1 over n sum over I of the indicator of xi less than or equal to x, right? So this here, we're going to call that f hat of little x, right? And so this empirical CDF is going to be pretty useful in checking what type of distribution we have. And in particular, we're going to be able to make plots related to this empirical CDF. And the plots will help us check whether a variable is in a particular family. So related to the empirical CDF are what are called the quantiles. So the let's call it the alpha quantile of a distribution is equal to the number x alpha where the probability that x is less than or equal to x alpha is equal to alpha, right? So in other words, the 5% quantile is the value of x such that only 5% of samples are going to be smaller than that. And the 95% quantile is going to be the value of x such that 95% of samples are less than that value. All right? So the CDF and the quantile are related to each other, right? Because if you take f of x, that's going to be the quantile at which x lies. right? Said another way, that's equal to fraction of future samples that we expect to be smaller than x. Right? So f of x gives you the quantile at which x lies, and then similarly, if we take a quantile x alpha, f inverse of x alpha, so we apply the inverse of the CDF to a quantile, that gets us we apply f inverse to alpha, that's going to be equal to x sub alpha, right? So in other words, if we apply f to a quantile, so in particular, f of x alpha is equal to alpha, right? That's the same as this. So if we apply f to a quantile, we get the percentage that quantile corresponds to. Similarly, if we apply f inverse to the percentage, we get the corresponding quantile. So we can go and we can do that with the empirical CDF, right? And we can say well, we can compare distributions by comparing the quantiles that you get from the empirical CDF with the quantiles that you get from a CDF that you think it might have, right? So we could take in particular, we could say, for alpha equals, 0.01 by 0.01 to 0.99, right? So that's 100 different points between 0 and 1. We could say that x1 is equal to f, let's say the normal CDF, the inverse normal CDF applied to alpha, right? That's what we would expect the alpha quantile of a normal distribution to be. And then we can say x2 is our empirical CDF inverse applied to alpha, right? And that's what our empirical distribution function says we would expect the alpha quantile to be, right? And then I guess we should, after computing these, we should store them. So maybe let me well, I'll just write pseudocode add x1 comma x2 to apply. Right? So what is this going to do? This is this produces something called a QQ plot, or a quantile plot, right? So we're going to get the alpha quantile that we would get under whatever distribution we're thinking about, maybe a normal distribution. We're going to get the alpha quantile under our empirical distribution that we estimated up here, and we're going to compare them. And that's going to look something like this. Let me put the plot up. So here what I've done is I've taken a distribution that is approximately normal, and I've plotted the normal quantile, that's x1 here, versus the observed quantile, that's x2 here, right? And if this is a straight line, the two distributions match up. The predicted quantile and the observed quantile are approximately equal. And you can see that this is approximately a straight line. And if I generate another sample, sorry. So here's another sample, right? And I can keep generating more samples, and you can see that this distribution lines up fairly well. It's typically quite close to being the quantiles line up quite closely with a normal distribution. Whereas I don't have this example prepared ahead of time. If I were to compare the quantile to something different, let's say a power law distribution, I would get that the two distributions look, the two quantiles look very different, and the line would not be anything close to straight. So what does that mean? That means that if you have some guess at what the distribution might be, you can make one of these quantile plots and check whether you get a straight line. And if you do, then that means that you are in good shape. You have your guess at what the distribution is correct. And if you don't get a straight line, if you get bad deviations from being a straight line, then that means that you should guess again at what the distribution might be. All right, so I think we'll end there. My office hours start now. I'll be here at least until 3:30, and longer if people are still asking me questions at 3:30. Again, please feel free to ask questions on Piazza or on Hangouts, and about either the lecture or the homework, the exercise that you guys are working on. All right, thanks a lot, and I'll see you guys on Wednesday.